Welcome to this part of fundamental of differential equation. In this part, we will understand the concept of the conservation, laws of conservation, that's the conservation of mass, energy, and momentum, and we will have a simple application to some fluid mechanics problem, just to practice for FE exam. Okay, so let me start. So any modeling application, physics-based modeling, will be is based on the laws of conservation. So there are three main conservation laws. So the laws of conservation basically for three fundamental properties. This is mass, energy, and momentum. The law states that the amount like this fundamental uh, quantities or amount cannot be created nor destroyed. They can just be transferred and transformed. So mass cannot be created nor transformed. It just can be transferred or transformed. And as I will show you in this lesson, that all these physics-based, most of these or almost all these physics-based models will be based on these laws of conservation. And the laws of conservation, they just boil down to something very simple, as you see in this screen, like increase minus decrease is equal to change. Like, what does this mean? Like, can we see an example from this? Yeah, so an example would be, simple example, in flow minus out flow, that is equal to change in storage. Yeah, simple. Like if I have, let's say, input here, let's say 8 unit, yeah, and I have output here, let's say 5 units of whatever that is. Then what would be the change in storage? The change in storage would be 3 plus 3, because the input is 8, the output is 5, then the change in storage would be 3. Sorry, would be 3. It is that simple. All the model, as I will show you, like the physics-based models that we'll be doing, is just based on this simple rule. Like change, like this simple rule, like because the conservation laws, we can put them in this simple mathematical rule. We can do this in we can do this with varying in time. Like we can put like a time component to it. So this is just one shot, yeah. But we can put a time component. Like if I divided everything by time, so in flow divided by time minus out flow divided by time equal change in storage divided by time. What does this mean? This means that like I'm now looking at the inflow rate and the outflow rate, and that would be equal change in storage. Inflow rate like Q in, yeah, negative Q out, that would be change in storage. Remember like this dot notation, we talked about this before. I think when we did some lessons in calculus, I told you like S, for example, that's distance. ds over dt, that would be like velocity, which you can also express it as S dot. uh, the S square dt square, that's like acceleration, which you can also express it as 2 double dot. Yeah, so you remember something like this. So basically, v dot, that is v over time. the change in volume over time, change in storage, dV or dV or volume here, dV over dt. Yeah. Okay. So basically, that would be if that is like a changing in time. So at time like 1, we have this. Like at time 2, maybe we have like 5 units entering and 5 units exiting. Then the change in storage would be like 0. Maybe like this is 5 units exiting. So here 5 unit entering, 5 unit exiting. So here that is like a changing with time. Yeah. At time 3, you might have 8 unit entering and 10 unit exiting. Then the change in storage will be like here is like 8 and here is 10, then the storage will be -2 and so on. So that would basically be in transient state, yeah, or in like a time varying, yeah. It would be like time varying, but it is the same rule. Increase minus decrease is equal to change. That is the fundamental rule of the conservation of mass, energy, and momentum, and that is the fundamental rule for physics-based modeling. So here, this fundamental rule, let me tell you, like increase minus decrease is equal to change. Yeah. So this fundamental rule, if you are looking for mass in, for example, negative mass out, that's equal accumulation or loss of mass. That is the conservation of mass. The conservation of mass, that basically you have, for example, the continuity equation. That's a form of the conservation in mass. Conservation in mass in water resources, it's used to model, like, for example, water balance in a reservoir or watershed or a hydraulic system or water flow in pipes and channels. That's all based on this principle, the conservation of mass principle. All pollution transport in water bodies, like in rivers or lake, or mass balance of a chemical reactor. That is, and I will show you in next lesson, like how from this you can drive the groundwater flow equation. Yeah. So that is the conservation of mass. It's all based on this simple principle. Yeah. Increase, decrease is equal to change. Yeah. Conservation of mass. So conservation of mass, energy, that would be Bernoulli equation, for example. So that would be the Bernoulli equation. Engineering application would involve, for example, energy balance in fluid systems such as pumps and turbines. So you are designing a water distribution network and you want to add or remove energy to increase like your pressure or reduce your pressure in the system. Yeah. So that would be like energy in, energy out is equal to accumulation or loss of energy. Yeah. And that's example for this would be Bernoulli equation. Example for this would be continuity equation. Bernoulli equation. Yeah. Then momentum. Momentum in, negative momentum out is equal accumulation or loss of momentum. Example for this would be, for example, fluid forces on structures, such as like the impact of water on dam or effect of wave on coastal barriers. So that will be all has to do with momentum, the conservation of momentum, like checking forces on dams or impact of flowing water on a bridge piers or other structure or whatever. That would be the conservation of momentum. Yeah. Uh, so these are the conservation of energy, and it is all based on like this simple rule. Yeah. So let me show you how this forms the basis of modeling application or any modeling application, physics-based modeling that we will be doing. It's based on this simple rule and this simple conservation rule: conservation of mass, conservation of energy, and conservation of momentum. momentum, yeah, and conservation of momentum. So do you remember we have this fundamental theorem of calculus, and basically it tells you this is like your surface integral and this is your volume integral. So basically it's telling you what this is telling you, what is like entering, for example, like through this surface and leaving through this surface, like the net flux through like surface, let's say like B and A, is equal to the change in flux inside this volume. So inside like your control volume, like inside this volume here. Yeah. That flux entering through the surface is equal to the change of flux through the volume. Let's look at it in terms of conservation of mass. So I will just replace this u function. Yeah. I will replace this u function with rho v, conservation of mass. And here v is velocity. And so basically, I will just replace this u with rho v, and this is a vector. And same here. So basically, like what I'm telling you here, yeah. So I will, and then here that would be my surface. Like let's say this is, I will call this like surface 2, for example. I will call this surface 1, and that here, this is my volume. What is inside like this surface? That would be my volume. So I'm replacing here this guy. Yeah, that's like my surface integral, and that is my volume integral. And you can go back to the previous course about the fundamental theorem of calculus. That's the fundamental theorem of calculus. Yeah, and what this is telling me basically here, so I can expand, like remember this is an indefinite integral, like so you remember we learned this in integral calculus, like indefinite integral, how to expand this guy. So like this would be like the integration of like this guy minus this guy. That's how you expand this like indefinite integral, if you remember this from uh, integral calculus. So basically this would be S2 minus S1, and here I will be this integration, I will be integrating through this surface area. So here this is like the surface area here, that's, and this surface area here, that is like my S2, and that is my S1 here. Okay, and that's my rho v, and that's a unit vector, and this unit vector is pointing toward is pointing always outward. So like this unit vector here will be pointing in this direction, so that would be n1, let's call it, and this would be like here n2, because it's always pointing. This is a unit vector, so this is a vector and this is a vector. Yeah, so basically what this is telling me, what this left hand side is telling me, this is my net flux, which means like what is coming from this side, let's say 8 for example, and this would be what is like the integration of everything that's coming from this side. So all this side I have like 8 units coming, let's say here, and what is leaving at this side, let's say 10 for example, 10 units leaving. So this would be like if I did this integration along all the surface here, let's say I will get 10. If I did this integration along all what is coming in, the fluxes that's coming in, I will get here 8 for example. Yeah, and we can change, we can check the unit of this. So let's check the unit of this to rho. That is rho, that is here, because this is, I'm here representing the change in mass. So like remember, uh, density is equal to uh, mass over volume. Yeah. So what is the unit of rho? That is mass. Yeah, mass over volume. What's the unit of this guy? That would be like mass. Yeah, over volume. That's like L cube. Velocity, what's the unit of this guy? That's length over time. This is unitless. This is just a unit vector. So it's unitless. And dA, that is like L square. So if I got this, this will go this will cancel with this. And then I got here mass over time. So basically, this is basically telling me how my mass is changing in time across this boundary. Well, how my mass is changing in time across this boundary will basically tell me how much is being stored or depleted inside, which is the second uh, term of my equation here. That's basically tell me what is stored inside. So let me delete this. Yeah. So just like the unit of this guy, yeah, that's mass over time. And that is basically telling me what is being uh, added or removed inside. So I have something coming here, something leaving here, and the difference, the net flux would be what is it changing, like what is increasing here or like decreasing here. So I have positive, something like the storage is increasing or my storage is decreasing here. Remember, it's all very simple rule. That's the simple rule. Increase, decrease is equal to what is it changing here. So like this term here, like the increase and the decrease, yeah, that would be like these two guys here. So this guy and this guy, that would be like this guy and this guy. And the change here, that would be like this guy here. Yeah. What is it changing inside my volume? That is this guy here. So this is just a mathematical representation for what we've seen previously. So this is basically telling me what is it changing inside this volume. And do we remember we studied this before in what? So we studied this in integral calculus, and we studied this guy, remember the diversion in differential calculus. So in differential calculus, we studied this guy. Do you remember diversions? This guy, this is a vector, which is like dc, sorry, d over dx, d over dy, and d over dz. Yeah. So sorry, that's the gradient and and dot. So that's the vector dot product, another vector that will give you like the divergence of your velocity vector. And if you remember from differential calculus, that guy was equal to something like this because the product, that's a vector, like this guy here. This guy is a vector, this guy is a vector, and if you check your differential calculus, the product of these two vector will give you like this scalar here. Yeah. And let's check the unit of this scalar here. So like the unit of this guy, let's check it. Let me write it down here. So the unit of this guy, that would be like rho. So that is mass over volume, L minus 3. V, that is length over time, divided by X, that is length, and dV, that is like L cube. So this guy will go away with this guy will go away with this guy, so I end up with mass over time. Same as here. So you see, so this guy also change of mass with time. Okay. So basically, like you see from the fundamental theorem of calculus, we can, on our way to derive the conservation of mass, the law for the conservation of mass, which is basically telling you what this is telling you let me just explain what this two terms. So let me delete this, let me delete this, let me delete this, delete all this. So let me just tell you here, this is mass over time. Yeah. What this is telling you basically, okay, the first term here, which is like this guy, yeah, is telling you that the net mass flux across the boundary. So I have a, let's say like this boundary, yeah, and I have this boundary. So it's telling me the net mass flux across this boundary, as expressed by this relationship, is equal to or not equal. It is equal to means what? Means it is the same as the net mass flux expressed as an integral inside this volume. That's basically what it means. So like my net flux across the boundary, like what's coming in and what's going across the boundary, is equal to what is changing across the boundary. So if 10 is entering here and 12 is leaving here. So what is changing across my boundary is like -2. So you see like the net mass flux is, sorry, so I have like 10 unit entering, yes. So this is, so that's -2. So I have like, so the change in, what is the change that is inside my volume is -2 because I have like 10 unit entering and 12 unit leaving. So that's -2, and -2 is equal to -2. So basically that is what this relationship here is telling you. Yeah. This is what this relationship here is telling you. So this one means, what this one means is the net flux expressed as the internal integral inside the volume. So like the changes inside here, yeah, the changes that are happening inside this volume. Okay, and uh, and from this we can, so basically we can get to this relationship, like what is the net flux across the surface is equal to the net flux that is happening inside my volume, and that's equal to what? That is basically what leaves here, like I have this negative sign to just indicate that something is leaving. Like what leaves is what is depleted inside. Basically, these two are the same. Like what is leaving, yeah, my system. So I have something that is left my system, that's equal to what is depleted inside this volume. And that is equal to the net flux. And here that will have the same dimension, because this is, let me show you the dimension of this guy. So the dimension of this guy here is 1 over T, and here is rho, which is like mass over L square, and this is delta V, that is like L square. So I got like mass over time. So let's read this again. This guy is telling you the net mass flux across the boundary here and here. That is the same as the net flux expressed as integral volume inside here, like what is it changing inside here. And that is the same as like what leaves inside, what is leaving from my system is equal to what is being depleted from my system inside, from what is inside my system. Okay. Uh, so, and from this fundamental theorem of calculus, yeah, uh, which I just showed you here, we can get to this laws, we can express this laws of conservation mathematically. So here, this is my volume integral. What is it changing inside my volume? Plus what is happening across my surface. Here is not equal to 0. Here is equal to m dot. Again, that's like mass over time, or the delta m dot. I showed you this before. Delta mass over delta t. This is like a more general form. That's like is equal to some source and sink term. If there is no source and sink term, that would be equal to 0. Yeah, but this is like a more general term. Okay, so what is, and again, this equation, let's just put this for now is equal to 0, not at its general form. This equation is the same as this equation here, or like this equation here, the same. Like increase minus decrease, yeah? That would be like this part, like my surface integral, is equal to change in storage. That would be equal to this guy here. Plus, if I have any sources or sinks there, so I can keep it in the general form here if I have any sources or sink there. And from this equation, actually, this is the general form of something which we have used before, which is the continuity equation. So remember, like the continuity equation, this is just a special case from this one. Similarly, we can do a similar derivation for the change in energy. It would look similar to this. Yeah, again, you have volume integral, you have a surface integral, and that would be equal to like here Q, for example, in that case. Q here would be the rate of heat transfer into the system. W here would be the rate of work done by the system. And your E here, that would be the specific total energy. So that's your internal energy, energy due to pressure, changes, kinetic energy, and potential energy. Okay, and similarly, you can do similar one for uh, changes in momentum, and that would be equal to your changes in forces. Yeah. Okay, so that would be that is total forces acted on the control volume. Yeah, that would be the total forces act. And a special case of this one would be what? The Bernoulli equation. Special case of this one would be the Newton law. So what we like, what we did before, like when we study fluid mechanics, when we studied the hydrology and hydraulics, and we solve like groundwater hydrology, and we or structural mechanics or dynamics or whatever, uh, we generally like use this simple form. But when we are interested in modeling application, we use the general form because in modeling application, this is only in a steady state where there is no change in time. But in real modeling application, in real system, we have something that is changing in time. And in real modeling application, like let's say, it's a like groundwater equation, for example, flow equation can be derived from this. So let's say this is my model domain. In this model domain, I am interested in like what is happening in each of these cell. Yeah, for example, like each of these cell, like what is happening in each of these cell, what's happening inside my system. Here, the change in volume. And I'm also interested in what's happening as a boundary, like something is entering or leaving my boundary, this boundary. So, so I'm also interested in this. So that's why I need this general form. I need to know what is happening inside my model, like this guy, and I need to know what's happening at the boundaries of my model, like this guy. And so there could be also some sources and sink term, which is this guy. So I could have like recharge here, for example, or I could have ground pumping abstraction, water getting pumped out or water getting recharged. So that's why this equation forms the basis of any modeling application. Because a modeling application, this would we are generally interested in systems that are 1D or 2D or 3D that are changing in time. So they have this time component, and then they have this spatial distribution, and then they have this boundaries where things are happening at the boundaries, and then they have sources and sinks. And that is the general equation that we would be using, for example, when our modeling application is based on the conservation of mass. And the conservation of mass, there are many modeling applications that are, most modeling applications that I have done are based on the conservation of mass, based on this guy. So for example, groundwater flow, it is based on this guy. So I have a change in head inside my model. I have some changes at the boundary of my model, and then I have some sources and sink term. Contaminant transport is based on this guy. So that's the same guy. So I can drive the groundwater flow equation from this guy. I can drive the contaminant transport equation from this guy. Anything like modeling some microbial activity. So I did before some soil respiration modeling. Soil respiration modeling is based on the conservation of mass. So in soil respiration, what you do, you use like carbon, let's say like glucose, for example, yeah, and oxygen, and then what you produce like CO2 and like water, yeah, soil respiration. So that's conservation of mass. So I have like 6 carbon here, then I would need like another 6 carbon here. I have 12 oxygen here, then I have, then you just like, I put like 6 water here, and I put maybe, this is auto, and I put like 6 oxygen here. So now something like this, yeah, then I have conservation of mass. And then I use something called like Michel-Menton kinetic to model like the uptake of the microbe for this organic carbon and how they will like produce CO2. Yeah. So that's based on the conservation of mass, based on this guy. Yeah. Similarly, if you're doing something related to change in energy, similarly, if you're doing something related to changes in momentum. Yeah. So that is so I hope you see these are the fundamental principle of physics-based modeling, because whatever we are doing, this is either based on the conservation of mass. What's coming in is equal to like the net fluxes, what's coming in and what's going out is equal to what is changing in my system, plus any sources or sink term. What's coming in and going out equal to what is changing in my system plus any sources and sink term, and we are monitoring this not only at the surface, like at the boundary and inside my system, but this is also changing in time. And that is the general form for physics-based modeling. Yeah. So I hope you got the picture, and I hope now you see that the importance of the laws of conservation and how these laws of conservation can be derived from the fundamental theorem of calculus. Okay. And this is the basic, like if you understand this, you will, that's basically the basics of modeling applications that we do. Yeah. Okay. Here I just like, this is just an exercise. I want you to list some of the applications that for the conservation of mass, conservation of energy, and conservation of your momentum, some applications that you're interested in or something you have done before. So for example, something that I have done before would be designing a water distribution network. So you ensure that the flow rate entering and exiting the pipeline network are balanced. That's the conservation of mass. With related to the conservation of energy, something I did before was again designing a water distribution network where you have pumps, and that's based on a modified form of like Bernoulli equation, and where you have you add like some pump to increase pressure or like something like this. Yeah, so that would be the conservation of energy. Conservation of momentum example would be design structures that can withstand forces, such as like if you have a pipe, yeah, and there is like a bend. Oh, it was not right. Like, if you have like you have a flow uh, that's occurring here, and you have a pipe bend. Yeah, so how the flow will affect like your pipe, for example, like if you can stand like this forces, or like you design spillways or a weir or a dam, that will depend on the conservation of momentum. In a simple form, in like when you were an undergraduate student and most classes, that what this is the relations that you use. But when you do modeling, you will be using these more of these types of relation. Like you, from this relation, you will drive your the equation for what the physical phenomena that you are interested in. Okay, so I will show you in next lesson how I, from this guy, how I will drive the groundwater flow equation, for example. Yeah, and then use this equation to model flow, and then once you model the flow you can model the transport, and once you model, and then you can do your design purpose. Yeah, but let me just show you here, remember, like let me show you like how did we get like this guy here, yeah, from this guy. Let me show you how did we do this, like how this is a special case of this guy. Yeah, so we have this guy, we've seen this is the laws of conservation of mass, and this laws of conservation basically is telling you like what's going out of your system, which is equal to what's changing in your system, is equal to the net flux across your boundary, plus if you have some sources or sink term. Now, if there's no sources or sink term, then that guy becomes zero. Yeah, there's no sources or sink term. Yeah, then that guy becomes zero. If there is no accumulation, what does no accumulation mean? That there's what is coming in, like Q in, remember, is equal to Q out. That's no accumulation, no change. Here, remember this law? Let's go back here. What does no accumulation means? Like this guy, is equal to this guy, this means that there is no change. So if this guy is equal to this guy, this is called like steady state, like change. Like increase is equal to decrease. That is like a steady state. This means that there is no change. Like so, change here. If Q in is equal to Q out, this means that the change in volume with time is equal to 0. There's no change. Yeah, this is basically what it means. Yeah. So let's come here again to where we are. So here, basically, there is no change of volume. Like no accumulation means this guy is equal to 0. Here, remember, increase negative increase is equal to change. No accumulation means like this guy is equal to 0. I have only like these two guys. And these two guys, like the S compromises like S1 and S2. So S1, that's like my surface 1, and then S2, that would be my surface 2 here. So I can just like, and we know this, like I can express this as like my two surfaces. So here I have like one equation for this guy and another equation for this guy that basically will be equal to 0. Now, assuming that the fluid is non-compressible means that density is not changing, so I can get rid of this guy. And then basically I can do this integration. I can integrate this velocity along like this whole area. So if I integrated this velocity across this whole area, I can just assume like an average velocity across this area. This is like V1 across like area 1. And then I can assume an average velocity here like V2 across like these like area 2 here. That would be, so if I did this integration, let me just do it here. So I will get something like this. V, that's a vector. Remember, like bold means vector. Like if you something in bold, this means vector. Yeah. So that's why I make it bold. So V, yeah, says V1, N1, that's a vector also. That's dot product, and that would be like A1. Here, this is a dot. N1, remember, N is here, unit vector to the surface, and this is always pointing outward. So this is a unit vector to the surface, and by definition, this is pointing outward. So let me get rid of this guy here, put it here, A1. So N1 is, that is like N1. It's always pointing outward. This is like N2. Yeah, it's pointing outward. So N V1 N1 plus V2 N2 times A, that is equal to 0. Yeah. So I can, so my velocity, see my velocity vector here is in this direction. My velocity vector is in this direction. So let me draw this. So N1 here and V1 is here. The angle uh, between this guy and this guy, that's like 180 degree. Yeah. And V2 is in this direction and N2 is in this direction. So the angle, so theta here would be equal to 0. Yeah. And here theta would be equal to 180 degrees. So do you remember like how to the dot product of two vectors? So the dot product of two vectors, that's equal to like V1 N1 cosine theta, and theta would in that case would be 180 degree plus V2. If you don't remember like dot product of two vectors, that's fine. And that would be cosine 0. Yeah. So what do we got here? So for this guy, we got like negative V1. This is equal to 1, yeah? And this is V1. And this is cosine 180, that's negative 1. cosine 0, that is 1. Yeah. So what we got from here is I will get negative v1. Oh, sorry, I forgot to put my a here. Because remember, you're integrating this over a. So you have a1 and you have here a2. So I get like negative v1 a1 is equal plus v2 a2, that is equal to 0. So I get like v1 a1 is equal to v2 a2, that is equal to q, because my q is constant. Because what is coming in? Yeah. So basically, I have, this is an area, yeah, and this is a velocity that's coming across this area. So that's like q in, and that is like q out, and they are equal, yeah, because remember, that's like q. So q in is equal to q out equal to q anywhere inside your volume, because that is a steady state. Okay. Uh, so basically, we got like this equation, and let's see how we are doing in time. I think we are not bad. So let's do an example. Like let's just see this equation. But now you see how we started from. That's the important. Like the details here are not important. Like the most important thing that you need to learn here is not like the details, but like to see like this laws of conservation and how this the laws of conservation mass of energy can be represented mathematically, and how this, as I will show you later, will form the basis of your modeling application, and how from this you can get this simple relationship which you can use to solve simple problem. But if your problem is changing in 2 or 3D, and if your problem is also changing in time, and if your problem is also changing across the boundary, and if your problem has also source and sink term, then this guy will not be useful, but this guy will be useful, and that's how you build your models. Yeah. Okay. So let's just do some simple example, like so that's a simple example to practice this law, practice using this and practice for FE exam. Yeah. So water flows through a 30-meter inside diameter pipe at an initial velocity of 1.9 meter per minute. The pipe diameter subsequently reduced. So I have a pipe that reduced in diameter. So something maybe that looks like this, yeah. So here is 30 meter, here is 15 meter, yeah. Q is not changing, yeah, because like Q in is equal to Q out, yeah. The diameter before this charge. So V1 is given. So I'm giving like this is D1, and I'm giving like V1 is equal to 1.9 meter per minute, and here I'm giving this is like D2 is 15 meter, and I'm asking like what is D1, yeah. So that is simple. That's just the conservation of mass, the continuity equation, which is based on the conservation of mass. So now you know you probably solved this when you were an undergraduate student in fluid mechanics class, but you never know where this equation, let me write down the equation, like V1 area 1 is equal to V2 area 2. You never know where this equation is coming from, and you never saw that this equation has to do with calculus, the fundamental theorem of calculus. Yeah. But anyway, so we can solve this easy. So that should be like V1 area 1, that would be pi d square over 4 is equal to V2 pi d2 over 4. Yeah. So this will go away with this guy. And then I need to find like the V2. So V2, that would be equal to like V1, and that would be like D1 over D2 square. Yeah. So basically that is a relationship that I have, and so I can find like V2, V1 is giving like 1.9, D1 over D2, so D1 is 30, D2 is 15, so I'm getting here like, and to the power of 2, so I'm getting like 2 to the power of 2 here, so that's 4 times 1.9, that would be what, like 8 minus, so that's 7.6 meter per minute. Oh, I think this is a typo here, that should be 7.6. Yeah, because I think this is correct, yeah. So I will correct this typo, so that's 7.6 uh, meter per minute. Yeah. Sorry for these typos, and it's not easy to prepare so many slides and so many lessons. And I mean, if there's one typo here or there, that's okay. I think that should be okay. It's also the first time to do this, to teach this class. Yeah. Okay, so this is another example, like you can solve this on your own and then try to check. Like here is this example. It's very straightforward, like assuming a flow of like, so Q is given and diameter is given, but diameter is in inch and it's telling you what is the velocity. Yeah, so Q is equal to velocity time area. So this is given and it's asking you for this, but here you need to convert inch to meter. So that would be the trick. So again, these are things that you are required to practice, and that things will be like also in your final exam, because you cannot have a master in engineering and you don't know, for example, how to convert between units. So here you can look. So here, for example, that's how you convert between units. So I want to get the final answer is in meter per second, but here I have this meter cube per minute. So I have to convert this to second. Like how to convert this to second? You want to make this guy into a second. So 1 minute has 30 seconds, which means like this guy will go away. So I will have this is meter cube per second. Similarly, my diameter, this is an inch. 1 feet has 12 inch. So the inch here will go with the inch here. And 0.304 meter will have 1 feet. So the feet here will go with the feet here. So I will end up with meter square. Yeah. And meter square. So I get something like 0.94 meter per second. Okay. So that's basically how you can this is another example practice problem, and again, all these are FE exam, so you can practice for the FE exam. So let's see how we are doing in time here. I think we're doing okay. A river has a continuous water flow of between the two bridges that are meter apart, whatever. The upstream river has a cross section, so I'm giving you the upstream river has this cross section, so area 1 is giving as 100 meter square, uh, while at bridge, so this is area A, while area B is downstream is giving like 100 meter square. The increase in velocity between the two bridges is mostly nearly. So now here I'm telling you what is the increase in water velocity. Read this problem carefully. Like here I'm telling you what is the increase in water velocity. What does increase in water velocity mean? Remember, this means that VB, that is a change in velocity, would be something like this. That's an increase in water velocity. Yeah. So this is what is asking you. What is this increase? So, and that would be simple because that would be equal to Q. Q is constant because remember, like Q in is equal to Q out is equal to Q. So if you understand this principle, you will say, oh, this is easy. That's like Q is constant. That's like A, B, sorry, yeah, minus Q over A, and Q is given as what? 10 meter per second. So that is easy. So you just substitute here 10 over this area is giving us like 100 minus this is given over 150, and then if you solve with this, you'll get a number, and that would be the uh, increase in water velocity between the two bridges. Yeah. And here, this is so that's the solution here, and this is just some easy homework problem. Okay, I think that's it for this lesson.